So we prove this two lemma. So one is when we have a kernel perfect orientation, then we can show that something is f choosable for this f, where this f is related to this out degree. And another one is that once we have a bipartite graph and some proper coloring, then by using this proper edge coloring, then using this we can construct a kernel perfect orientation. Note that this proper edge coloring C is purely there to produce an orientation. So it doesn't matter how many colors we use on here. As long as it just produces a orientation, then the resulting orientation, this is kernel perfect. So number of colors that we use on this edge coloring has nothing to do with our final edge coloring, which can be obtained from the kernel perfect orientation. And using this now, we want to prove this statement for multigraph G. Recall that in undergraduate graph theory, we proved this inequality proved by Shannon for multigraph, which is best possible by considering this graph. So for each pair, we put the edge multiplicity delta over 2 in a triangular way. Then every edge must have a different color so that its edge chromatic number is 1.5 times delta, while the maximum degree is delta. So in order to prove this, we first want to prove this theorem. If G is a bipartite multigraph, and f is defined on each edge to be the maximum of the degrees on each endpoint, then the line graph of G is f choosable. So how do we prove this is, when you have xy, we want to find the orientation of this line graph. And this orientation we want to be kernel perfect. And for each vertex xy here, which is h here, we want the out degree of certain orientation here is at most the maximum of degree of x in this G, degree of y minus 1. So in order to get the kernel perfect orientation, we want to use the approach before. If there are several edges, then we give some proper edge coloring. And then that proper edge coloring C produces orientation DC as defined before. Remember, we have two edges with the number 1 and 2 and number say 3 on this edge coloring, and they are E1, E2, E3, then E1, E2, E3. Between E1 and E2, we orient from smaller one to bigger one, and between E3 and E2, we orient it from bigger one to smaller one. Then this is automatically kernel perfect. So that we don't have to consider anymore. But we want this to be satisfied. For that, we want to use some induction. Say induction on the number of edges. Then what you do is you take some edges and then you want to delete. Let's say deleted edges are m. Let's say m is a matching. Then you consider G minus m. And in this G prime, you use induction to find some C prime, which gives the value in here. And then we, according to this C prime, we can get the orientation which satisfies this DC prime. And here it's G prime. Here it's dg prime y minus 1. This is satisfied. And let's say deleted edges are E1, E2, E3, then E1, E2, E3. And once we have this induction, by induction we have this certain C prime which gives us the kernel perfect orientation, D sub C prime, which satisfies this. From here now we want to get back to the orientation of G, which means that if there is some edge from here to here, then we want to decide the orientation of this edge. And that orientation can be given by assigning some value here. For instead of this, we extend this C prime to C by assigning some value here. Again, recall that this C and C prime are purely there to create an orientation, so we don't care how many colors we use on this edge coloring. And this, as if this orientation is defined on the, which has a larger C value. So let's just, to make it simple, we can just give some large number on each of these edges on M. Then, by adding this back, adding this M back, for certain vertices, this might increase. For certain vertices, this might increase. And for certain vertices, this might increase. There are several kinds of edges. If there is some edge, E is outside, totally outside of this M, so it doesn't share any vertex with M, then in here, this E has no neighbors in any of these. So this stays same, and this stays same, this stays same. So this new, in the large orientation, this still satisfies, which is what we want. So this has no problem. And also, if some edge is in here, then this increase by 1, and this increase by 1. And then how much does this increase? Is that, let's say this is E1 and E2, and this is E. Then this E has two, because this blue thing is a matching, it has two neighbors only, E1 and E2. And then if this has large number, say 100, and this has large number C, and in the middle it has a small number, say 10, then by our choice it has E2 as out neighbor and E1 as in neighbor, so this also increased by 1. So these edges are also okay. And if there is this edge, E prime, then this E prime has only the neighbor, which is E2. No, not E2. Let's say, so here, yeah. It has only one neighbor, E2. Only one neighbor among this blue one. And it's actually oriented from E2 to here, because we gave the large number on the blue graph, blue edges. So this that means, give me a moment. In that case, it's from big number to small number. So it's this stays same, and this, x part stays same, and this part plus 1. So since originally this inequality holds, and then this didn't increase by including the black one, and this may or may not increase, so this edge is also okay. The only problematic edge is this, because in this edge, by the same logic, it has only one neighbor, which is E1. And in the large graph, because we gave this large number, it's oriented from here to here. So this out degree increased by 1, and dx increased by 1, but y part stays 0. So depending on which one is bigger, before this holds, and now you add this one, and you add this one, and you add 0, then we don't know whether the inequality is still true or not. It could be that this increased by 1, but by taking maximum, this could stay same. So this type of edge is dangerous in this induction argument. So for that, we want to prove this lemma. So that intuition motivates us to prove this lemma. In this bipartite graph, let's just assume that x is has at least size as big as y, and then no isolated vertices. Then you can find the matching whose vertex set is S union neighborhood of S for some vertex at X. In that case, if we take this M, and then we delete that, and then we do this argument, then we don't have any edges like this. This is S, this is N of S, which has the same size. If there is this purple edges, then N of S would have been bigger. So we can forbid this type of edges. So that motivates us to prove this lemma. And this can be actually proved in a non-difficult way.